Let's talk about space. What is it? The Hubble Space Telescope brought us views of galaxies from the visible horizon of our universe. Speaking generally, universe means everything, all that we see and cannot see. When astronomers speak of the universe, they usually mean the observable universe, what technology has enabled us to see, or what physical laws will permit us to see as technology advances. Astronomers usually measure the far reaches of space in light years. A light year is the distance that light travels in 1 year, which is around 6 trillion miles. Our farthest views of space have come to us from the Hubble Space Telescope, which was launched by NASA in 1990. Hubble revealed galaxies more than 10 billion light years away, or equivalent to 60 billion trillion miles away. Light in the form of radio waves has come to us from another few billion light years beyond even those galaxies. The illustration on the right is of our disc-shaped galaxy, the Milky Way. Even though we will never see it as a disc shape, like it's shown from this perspective, we can see it from our own perspective here on Earth in the outer bands of our galaxy. If you've ever stood outside where there's minimal light pollution at night, you might have been lucky enough to see that thick band laid across the sky. That's our Milky Way from our perspective. The illustration on the left, however, shows two galaxies colliding with one another. This is something astronomers believe our galaxy is likely to have happen, possibly again, billions of years from now. Our sun is about halfway from the galactic bulge in the center of the Milky Way. We revolve around the bulge every 250 million years, and we don't move just horizontally. Our sun oscillates vertically up and down, as well as moving around that bulge, and then we travel with it in a giant spiral through space. This scale model of our universe is for relative size only, not distance. At this scale, Pluto would be more than a mile beyond the edge of the screen. As with the term galaxy, the meaning of planet has changed considerably, and even more recently. For decades, a planet could be safely defined as any of 9 bodies that revolve around the sun. Outward from the sun, the planets' order is Mercury, Venus, Earth, and Mars. These are the terrestrial or Earth-like planets. Then Jupiter, Saturn, Uranus, and Neptune, the gas giants. And then the infamous Pluto. American astronomer Clyde Tombaugh discovered the icy misfit Pluto in 1930 and thus made possible a catchy first-letter memory aid. My very educated mother just served us 9 pizzas. In 2006, those who came to know the planets by thinking of 9 pizzas were stunned to learn that Pluto was gone. That is, members of the International Astronomical Union, the IAU, voted to strip Pluto of its status as a planet. Its demotion to, quote, dwarf planet was the result of the IAU's effort to give the word planet its first official definition. According to the definition, a planet must be an orbiting body large enough to become round by the force of its own gravity and large enough to dominate the neighborhood of its orbit. While certainly round, tiny Pluto is hardly dominant. If it were set down on the Earth's surface, it would barely cover India. The loss of Pluto was offset by the discovery of planets outside of our solar system. Since the time of Galileo, when the sun was found to be a star, astronomers have thought it was likely that other stars are orbited by other planets. The discovery of the first exoplanet came in 1995, and more than 400 have been spotted since. Most are gas giants and unlikely to support life, but this does not mean that these are the most common kind of planet, only that they are the ones least difficult to find. Planet hunters are focused on the possibility that some of them have moons that are more Earth-like than the actual planet itself. A moon is a natural satellite of a planet. Our moon is one of at least 90 in our solar system, almost all of which are beyond the realm of the terrestrial planets. Mars has 2 small moons. Mercury and Venus have none. Our moon is unusually large, about 1/4 the size of Earth. While it is enthralled to our gravitational pull, it is large enough to pull back. The moon's gravity slows our rotation and creates our ocean tides. The surface of the moon is, of course, the farthest out in space that we've stepped. Among the many firsts of the Apollo missions is that it was our first hands-on experience with the finite speed of light. The average distance to the moon is about 240,000 miles. Light travels at 186,000 miles per second. Moonlight, then, takes a little more than 1 second to reach us. This slight time lag was observed in the transmission of images from the astronauts to ground control. Light year measurement allows us to pack vast numbers into manageable units. It also helps us to think in terms of age. As the moon landing showed, nothing in space comes to us, quote, live. When we look out into space, we look back in time. The farther we look, the farther back we see. We see the Hubble Space Telescope galaxies 10 to 12 billion light years away as they were 10 to 12 billion years ago. That's how long the light has taken to reach us. We see those galaxies in an infant state at a time near the beginning of the observable universe, which has been dated at about 14 billion years ago. This image is of the Keyhole Nebula. The gas and dust of a nebula signify either death or birth, the remains of old stars, or the raw materials for new stars. Edwin Hubble is not the only scientist to have back-to-back hits, but 2 of his discoveries have done more to broaden our view of things than any others in the last century. After discovering other galaxies, he observed that they're moving away. More specifically, he observed a shift to the red end of their light's spectrum, a result of the Doppler effect. We all experience the Doppler effect as it applies to sound waves. A moving sound, like a siren or a train whistle, rises in pitch as it nears us and lowers as it passes. As it nears us, the sound waves shorten. As it moves away, the waves lengthen. A similar principle is applied to light waves. Red light has the longest wavelengths in the visible spectrum. As an object recedes, its light shifts to the red. Measurement of the redshift has allowed for measurement of the speed at which galaxies are moving away from us and from each other. Both physics and logic dictate that if galaxies are moving apart, they must have once been closer together. Dating the beginning has been a matter of running the clock backward to a first moment known as the Big Bang, when the observable universe began its expansion. If Big Bang seems too jokey a name for something so momentous, well, it's because it got the name from scientists who didn't believe it either. The idea was first suggested in the 1920s by a man named Lamontre, a Belgian priest and physicist who described the source of the universe as a primeval atom. Adherents of the idea have had to battle with misconceptions that the Big Bang was an explosion of this matter in space. Rather, it was a sudden expansion, and yes, a fiery explosion, of all space. Expansion is often described with homeanalogies of baked goods. For instance, we might imagine galaxies as blueberries and space as a muffin. As the muffin rises in the oven, the blueberries move apart and take their places on the top. The blueberries do not move of their own volition. The muffin, space itself, pushes them apart. Expansion does not mean that individual galaxies and everything in them, including actual blueberries, are spreading apart. The force of gravity holds galaxies and star systems together. The Big Bang Theory predicted that light from the earliest universe would not be visible through a telescope. On its long journey to reach the viewer, the light would lose most of its energy and diminish into radio waves, a less energetic form of light. These waves were discovered in 1965 in a comedy of coincidence. Two Bell Laboratory scientists, Arno Penzias and Robert Wilson, were engaged in a project that would relay telephone calls via satellite, working with a horn-shaped antenna in Holmdel, New Jersey. They were vexed by a persistent background noise that seemed to be coming uniformly from every direction. To get rid of the noise, they went as far as climbing into the horn with scrub brushes to clean it of pigeon droppings. Meanwhile, at Princeton University, an hour away, a team of scientists were working on ways of finding the Big Bang waves, called cosmic microwave background. Penzias and Wilson, unaware of this research, decided to call these very scientists for advice. When they described the situation, the Princeton scientists knew that they had been scooped. The noise that Penzias and Wilson tried to scrub away is an echo or afterglow of the Big Bang, which touches every nook and cranny of the universe. It comes uniformly from all directions because the expansion occurred in all space. In 1989, NASA launched the Cosmic Background Explorer to study this primal light. The studies found by the properties of the light correspond to what could be expected from light emitted by very hot matter about 14 billion years ago, the date of the beginning of the observable universe. With this question, science comes to an end for now. Astronomers can imagine the expansion of space as if it were a movie, and then run the movie backward to a split second after the Big Bang. In reverse, they can visualize all space and matter shrinking to a size so small that it might as well be called nothing. But they cannot know what caused the Big Bang, or address the question of how everything can come out of nothing. The questions beyond the observable universe are beyond what we know of physics, and so are open to anyone. Did the observable universe displace another universe? Was the Big Bang just one of many Big Bangs in a larger universe? And if so, what is this larger universe?